All right, so we're gonna get started with this video with the Intermediate Value Theorem, which we can also just refer to as IVT because it's Intermediate Value Theorem. And this is actually pretty important for a lot of points of calculus. So if you can just remember IVT and like kind of what it does, that's honestly probably all you need. But yeah, so what the intermediate volume theory states is that, if we have a function, let's call it f of x, and this function is continuous on a given interval. Okay, so we'll call this interval a comma b, and we'll use actual values later for examples for this, but for right now, this is just kind of the definition. So if we have this function, and it's continuous on this interval that they gave us, thinking about how to put the next part into words. It is continuous on this interval, and there's some number, we'll call it d, that is between between f of a and f of b, then there has to be, or then there exists, another number, we'll call it c, within that interval, where this is true. And what that really means is that, say, we have a continuous function on the closed interval from like x is 3 up to 12, right? If our function is continuous on this interval, and we know that f of 3 equals -2, and f of 12 equals 17, then I know at some point on this function, there has to be there has to be some x where the y equals any point between -2 and 17. So there has to be some x value, and we'll use c to represent that, where maybe our y equals 15, right? Because that's between this -2 and 17. And a good way of thinking about that, it's a little weird, but like the textbook actually says it pretty interestingly. Whereas if you need to cross a river, right, you either have to jump over the river, in which case your motion wouldn't be continuous, right? That's talking about if there's like a hole or a jump or a discontinuity in our function. You either have to jump over the river, or you have to walk through it, and you have to get a little wet. In which case, you have to go across all of these values from this -2 to 17. And we could say maybe our function looks something like this, right? And we're looking at it on maybe this interval here. This is a different example now. So obviously our function is continuous on this interval that I'm showing, and we're going to use, this is our a, this is our b. We'll say that maybe this is a y value of 2, right? So that's an a comma 2. And this is maybe a y value of a -2. So we'll say that's a b comma -2. And so on this interval, a to b, obviously inclusive here, I know my f of a equals 2, and my f of b equals -2. And we can see kind of visually looking at this line that it's going to cross every other y value on the way from this point to this point. And that's really all that the intermediate value theorem tells us, which is that we have to cross all of these values if it's continuous. Obviously, if it's not continuous, which is like our first big thing, we have to make sure it's continuous. If it's not continuous, then we could have maybe this hole here, and now we don't know that there has to be this value here. And so the intermediate value theorem wouldn't work here because there's that hole and that value simply doesn't exist in the function. All right, and on that note, I think we're going to jump to some question examples that I prepared. Hold on, let me just erase all of this because we'll need the space in a little bit. All right, and now over here, oops, goodness. Over here, we've got a few different questions, just to kind of reinforce the idea. This first one tells us that if this function here, g of x, is continuous, so we've met that first criteria, on the interval -1 to 5, so -1 to 5, good, then on what interval must there be a solution to g of x equals 3? And what this is asking is that, well, it looks like it meets our intermediate value theorem constraints, right? Because it's continuous on this closed interval. And we see what those values are. So if I look at our y values, it goes from 0 to 15. It's asking me on what interval can I guarantee that there will be a y value of 3 somewhere. And you could say on this entire interval, but we're going to get a little bit more specific because obviously we can't guarantee that there's a y value of 3 in this interval because from 4 to 9 doesn't have to cross paths with 3. It might, but it doesn't have to, right? Because if it was like a squiggly line, it might, but we can't guarantee it. So it's really only guaranteed on this interval. So our answer would be from -1 to 2. That's our answer for this one. The next one, same kind of deal. If f of x is continuous on the interval -8 to 0, which they've given us up here, it asks, then on what interval must there be a solution to f of x equals -3? So where can we guarantee that there will be a y value of -3 somewhere inside of it? And we look at this and we see it goes from -5 to 0, which doesn't tell us much. So let's look at the individual intervals we see here. So from 5 to 8, we can't guarantee there's a -3 in there because all we can really guarantee is everything between 5 and 8, right? -3 is not between 5 and 8. The next one goes 8 to 4, which also doesn't guarantee -3, and then 4 to 0. So it looks like the intermediate value theorem isn't actually useful here because we can't guarantee that there is a y value of -3 anywhere on here. So the answer to this question is none. There is no interval that we can find based on the information given that guarantees this solution. Now, this next one is, again, just more same practice. It tells us that h of x is continuous on the provided interval. It tells us h of 0 equals 2 and h of 4 equals -2. So we need to figure out which of these answers are guaranteed by the intermediate value theorem. So we know that the function's continuous, which is good because that's our first constraint. So now we just need to see if any of these offer a y value between here that are on this interval. So let's take a look at the first one. So there must be an h of c where that equals -1. Okay, that's valid, right? Because -1 is between -2 and 2. So that y value does have to get crossed at some point for at least one c between -2 and 2. And that actually shows us that this answer is not correct. This one's wrong. And the reason that is because it's saying that c is between -2 and 2. But -2 and 2 is our y values, and c is going to be that x value that we're looking for. So what we want to find is this first bit on this interval, not between these y values. So we're going to cross out this answer. And looking down, we actually see that there's that exact first bit on the correct interval, because our x goes from 0 to 4. So this one's actually going to be right. We're going to check this one. And now we're going to check this one and see if it works. So it says h of c equals 0 for at least one c between 0 and 4. So we see that the interval's right, because we're looking at our x values, which is good. But let's see, is 0 guaranteed by that range there from -2 to 2? Yeah, if the function's continuous like they say it is, we have to cross 0 at some point to get from our negative number to our positive number. So this one's also going to be correct. And then finally, we've got some some x value, c in h of c, that makes a y value of 3 for at least one c between -2 and 2. And again, this one's wrong because of this is the range and not the domain. We want to be looking at c in terms of x, not our y. But we can also see that this one's wrong, even if we didn't get to that part, because 3 actually isn't guaranteed in this case, because from -2 to 2, well, 3, you're not going to cross 3 anywhere on the way from -2 to 2, because 3 is going to be after 2. So that 3 is not guaranteed, and this answer is wrong. So our answer would just be these two right here that we checked. All right. Now we're going to move on to what the bisection method is. We're not going to jump into that practice immediately. I'm going to kind of explain it a little bit. And the bisection method is a little tricky to wrap your head around just at certain parts. And so the bisection method actually depends on the intermediate value theorem. So if you don't understand the intermediate value theorem, sorry. So if you don't understand the intermediate value theorem, you're going to have a hard time with bisection method. So if you're confused at anything that I just went over, again, Khan Academy and Google are your friend. So our teaching assistants and whatnot, and you can always rewind and go watch over that again, just in case that helps. Anywho, the bisection method is used to find the roots or zeros of a polynomial based on the intermediate value theorem. So what it tells us is maybe if we have this function, right? Or this isn't a function, this is a chart, sorry. Maybe we have this function. We see it has a 0 there, but we don't know exactly what that x is. We don't know where that, or we'll use c, actually. We don't know what value that's at yet. All we know is there is a 0, and we don't know how to find it. So we'll call this function f of x. And again, this function is continuous. We'll say it's on this interval from a to b. And what we find there is that when we plug in f of a, we don't know what number this is just because we aren't actually using a function right now, but we will in our examples. But when we plug in f of a, we see that this is going to be a negative number. So I'm just going to put a negative sign there so that we know that. So we see that that's a negative number. And when we plug in f of b, we see that it's a positive number. And that's all we really need to focus on. We don't really care about what number we get when we plug those two values in. We just care about whether or not they're negative or positive. So what this tells us is that on this interval, I go from negative to positive, from a to b, which means that at some point we have to cross 0 where it's not going to be either of those, right? Because if we have a negative number, we have to cross 0 to get to a positive number if the function's continuous. Just like the intermediate value theorem shows us. I keep saying theory. And this is all that we really need to worry about. So what the bisection method is that if this interval is, like, if this is the case on this interval, that one is negative and the other is positive, then we can estimate about where this zero is by cutting our domain, or our interval, in half. So we see we go from A to B. So I'm going to cut my interval in half. So now I'm going to go from maybe A to whatever half of B was. Or that's a little tricky to show without using actual numbers here. Oops. But we cut that interval in half, and then we plug in f of whatever that is, and we hope that it gets a 0. If it does get a 0, good, done. We found our 0. If it doesn't get a 0, then we just keep cutting our interval in half. So maybe this wasn't our 0. Maybe our 0 is over here or over here. We'd have to cut our interval in half again, and this would be our new interval, and then again before we got to our 0. And sometimes we won't ever get like an exact 0 on that interval. So the bisection method is mostly for just approximating it really close, just getting a really good estimate. And I think that's pretty much all that the bisection method is. It's really tedious. It's a lot of just writing out steps and trying not to lose any numbers or signs anywhere. The only other thing that I want to cover with that is this thing called tolerance. And so what tolerance is with the bisection method is, say I wanted to find a 0 of a function. If I want to find the 0 of f of x, and I have a tolerance of maybe 1/16, or we could use a decimal here even, like 0.05, so 5/100ths. That tolerance tells us that we have to have a maximum error of this. We have to be under that number with our maximum error. And we'll kind of go over what that actually means with our examples. I just wanted to kind of introduce that before jumping right into them. So let's take a look at this first piece of practice over here. So it says approximate the root of this function within 1/100th accuracy. So this is our tolerance that they gave us. And so what that means is that we first need to find an appropriate interval to use. And give me one moment because I just dropped something. Okay. Let's see. So we first have to figure out an appropriate interval. So I would just plug in maybe a couple values, kind of see where they take us. Let's try plugging in f of 0. Obviously, f of 0 is going to get us a -3. Okay, so we get a negative number. If I plug in maybe an f of 2, that gets me a 4 minus 3, which is 1. This is good because one of our values is positive and the other is negative. So we can use this interval of of 0 to 2 because this is going to be negative and this is going to be positive. So we're first going to check on this interval. And right now, the maximum error for whatever we find in this interval is going to be, and maximum error is 1. And the reason that that's 1 is because if I cut this in half, whatever value that's going to be is going to be 1 away from those answers. And the reason we do this is because obviously we don't know that cutting it in half is going to get us to our 0, because functions are interesting like that. They could be like that. We never know. So they, like, our 0 could be, or our root could be really close to x equals 0, or it could be really close to x equals 2, or it could be smack dab in the middle. We don't know. So our maximum error, the farthest away from wrong we can be, is 1. What we're going to do now is we're going to cut this interval in half. So halfway between them would be 1. So we're going to plug in f of 1. f of 1 is going to be 1 squared minus 3, and that's going to be a negative 2. Okay, and I think, let's see, we said f of 0 was negative 3, and f of 2 was 1. So it's still a negative number, and it's not our 0 yet, and it's not within that tolerance. So because it's our negative number, we're going to replace whichever one was negative with that x value. So our new interval is going to be this 1 to 2, because if we plug in a 1, we get a negative 2. If we plug in a 2, we get a positive 1. So we know that there's still a 0 on this interval. Now, our maximum error is going to be 1/2, right? Because the distance between 1 and 2 is 1. So if we cut it in half, there's only 1/2 away from how correct they could be. And that's kind of why we use the plus or minus when we talk about our tolerance. But let's keep going. So now we're going to cut it in half again. So now we're going to plug in f of 1.5, which I'm actually going to use fractions for this because it's a little easier for me to do in my head. So 1.5 is 3/2, which would be 9/4 minus 3. 3 is the same as 12/4, so this gets us negative 3/4. So still a negative number, and we're kind of closing in on that 0. So we're again gonna replace our whichever one is our negative with this new x value, which is this. And now our maximum error is a little different, right? Because these are, now this is 1/2 away from being 2. So our error is going to be half of that, or 1/4. And we just keep doing this until we're within the desired tolerance. We're not quite there yet, so we'll keep going. And we cut this in half, so I have to add 1/4. So that's going to be 7/4. That's going to be 49/16 minus 3. And 3 in terms of 16ths should be 48/16. So we get 1/16. Oh, and this one's positive now. So we're not going to replace this x value with it. We're going to replace our positive one. So now it goes from 3/2 to 7/4. And now our maximum error is cut in half again, and it's going to be, I believe, this. And we just keep going. Let's see. So halfway between 3/2 and 7/4. Okay, so that's the same as 6/4 and 7/4, or 12/8 and 14/8. So we want to plug in 13/8. And obviously bisection method, we're allowed to use calculator typically. So I don't have to be using fractions right now. I could just be plugging this into my calculator. But for the sake of neatness on our page, I'm just going to use these fractions. And so if I square that, because that's our function, right? I get 169/64 minus 3. 64 3 times is, I think, 192/64. And that gets us a negative number. What negative number is that? That's going to be negative 23/64. Okay. So we are, oh, sorry. I didn't mean to write that. So we're going to replace this x value with the one we just plugged in, because that got us a new negative number. So, no, I was right to do this the first time, because that's our x value, right? And this is the domain that we're looking at. So it's from 13/8 to 17/4. And now our maximum error is, let's see, I believe it's that. So we're really closing in on it. We need to be within 100th accuracy. And we're getting close there. So let's try another So let's see, between 13/8, let's see, it's 26/16, and that's going to be 28/16. So 27/16 is going to be our next x value that we plug in. And that is a little trickier to do in my head. So it's going to be 729 over 256 minus 3, which will be that, which gets us a negative 39, 256, which is another negative. So again, we replace this one because that happens to be the one that results in a negative. So 27/16 and 7/4. And now our maximum error is, let's see, what is, oh Lord, okay. Hold on. So let's see, so that's 27/16, and then that's, what did we say that was? 28/16, so they're 1/16 away, so our error is going to be 1/32. And we're really closing in on that tolerance there. And yeah, so I think we could do this 2 more times and be within that desired tolerance. So let's try that, as admittedly terrible as this is. So that's, let's see, it's 54 out of 32, and that's 56 out of 32. So I want 55 out of 32. Which is getting us some pretty big numbers. This is rough. Okay. So it's gonna be this over this, which is awful. And we're subtracting 3, which is this. Which is a negative number, which the fact that it's negative is really all we need to know. So let's see that we're going to replace this one again. So and now our error is, I believe, this. And for the sake of time, actually, I'm going to call that it. I do have the answer written down. So if we were to do this one more time to be within the desired tolerance, our 0 would be approximately at this decimal here. That would be approximately where our 0 is, based on, like, to be within this total accuracy. Let's skip that one. Let's try number 3 now, and then I think we're actually gonna end the video, because this is, I know it's kind of grueling, but we do have to know it for our class, unfortunately. So this one's interesting just because it doesn't start out with an f of x. We've got x on both sides. So what we need to do is we need to set that equal to 0, because we're trying to find our roots, right? So this is going to turn into, let's see, an x cubed, and we subtract this from both sides. So we get x squared. And then we're just moving everything to this side. So I subtract my 9x squared. And then I'll add this 2x to my 18x, which is 20x and subtract 7. Okay. So what we want to do now is we want to come up with an interval that we think this might work on. So let's try plugging in a 0 to start. So we're going to call this function f of x still, just for the sake of writing it. So f of 0 is going to be a negative 13. Let's try another number. Let's say f of 2 again and see what that gets. So it's going to get 2 cubed, which is 8, minus 9 times 2 squared, or 36, plus 2 times 20, which is 40, minus 13. So that's going to be, let's see, that's 8 plus 4 minus 13. Oh, that's a negative 1. So because these are both negative, we can't use this domain, or this interval, sorry, because we can't guarantee that there's a 0 in there. So let's try something. Oops, don't want to, oh no, I don't want to erase all of that. I do want to erase this, and I want to erase this. Let's try maybe f of 3. So 3 cubed, that's going to be 27, minus 9 times 9 is 81, plus 60, minus 13. Oof, this might also not work out super great. So it's 27, minus 21, minus 13. That's also a negative number. Not really working out in our favor, huh? Let's try a negative number then. Let's try maybe f of negative 1. That's going to be a negative 1, minus 9, minus 20, minus 13. Obviously, that doesn't get us very far. So this one has us a little stuck. Maybe we have to go bigger. I'll try 8. That's going to be a bit of a pain. Just a little bit, though, so it'll work out, I'm sure. So 8 cubed, that's 64, 512, minus 9 times 64 is 576, plus 20 times 8, which is 160, minus 13. Well, let's see, it's going to be a negative 64 plus 160 minus 13. That's going to be 96 minus 13, which is just 83, which is a positive number, which means we've got an interval we can work with now. It's a pretty big one, right? Because it spans across 8 different numbers, but we're going to work with this. We've got 0 to 8. And so we're first going to plug in, we're going to cut that in half. So we're going to plug in f of 4, which should be 4 cubed is going to be 64, minus 9 times 16 is 144, plus 20 times 4 is 80, minus 13. And we can condense this a little bit, so it's going to be negative 80 plus 80 minus 13. So those cancel out. It just ends up negative 13. I think that's right. I'm not. Oh, that's funny how that managed to be the exact same as our f of 0. But because it's negative, we are going to replace the x value that gets us a negative number with it. So now our interval is 4 to 8. And, oh, I forgot to write our error. This one is out of 4. Now this is an error of up to 2. And now we're going to cut it in half again. So we're going to plug in f of 6. And that's going to be 6 cubed is 216. Minus 9 times 36. Plus 20 times 6, which is 120. Minus 13. Which, let's see. So if I add these positives, I get 336 minus 324 minus 13, which gets me 12 minus 13, which is a negative 1, which we're really closing in on that 0 now, aren't we? So negative 1, and again, this is negative, so we're going to replace this x value here. So it's going to go 6 to 8, and now my maximum error is plus or minus 1, which is good. I'm glad that our error halves. So now we need to plug in f of 7. 7 cubed is going to be 343 minus 9 times 49, and then 20 times 7 minus 13, and I'm just going to go ahead and use a calculator to condense that. That's going to get us a positive 29. So we're going to replace this 8 now. So now I've got 6 to 7 with a maximum error of give or take 1/2. So now we're going to get into some ugly numbers. We're going to plug in 6.5, and I'm just going to do this with a calculator this time. So 6.5, and that's cubed, minus 9 times 6.5 squared, plus 20 times 6.5 minus 13 gets us 11 and 3/8, which is positive, so we're going to replace that 7 with it. Okay. Oops. So now our error is getting close to where we need it to be, and we're going to cut that in half. So now we're going to go 6.25. And again, I'm just going to use a calculator to condense that for us right now. So that cubed minus 9 times 6.5 times 6.5 plus 20 times, oh, not 6.5, I was messing that up. Whoops. So it's 6.25 cubed minus 9 times 6.25 squared plus 20 times 6.25 minus 13. That gets us 4 and 37/64. So we'll plug in that there, and that gives us an error of roughly this. So one more and we should be within our desired tolerance. So now plug in 6 1/8, which is 6.125. Plus 20 times that minus 13, which gets us big fractions now. That's still positive. So now we have this interval with a maximum error of this, which is 1/16, and that is less than the tolerance, so it's within this tolerance here, which means that our answer for this problem is just going to be whatever is smack dab in between there. So now let's see, that's going to be 6 1/16. And again, I'm just going to plug that into a calculator. So, and that gets us about, well, I could use the fractions to be exact. and that's going to be about this. This is approximately what our 0 is, with an x value of 6 1/16, and you see this is really, really close to 0, right? So that tells us we're probably on the right track, and that is within our desired tolerance. All right, so that's all that we're going to do on intermediate value theorem and the bisection method. Remember that bisection method kind of depends on intermediate value theorem a little bit, because otherwise we have no way of proving that if one of them's negative and the other's positive, there must be a 0. That only works because of the intermediate value theorem. I will be uploading another problem set video soon. And yeah, that is it for today. I hope that this was helpful.